All right, so now it's time to talk a little bit about why we're discussing these linear systems and why we are solving these guys. What uses can they be and can they have, and what situations are we going to want to write a linear system? Now, we're taking a look at a couple of situations already, but some real clear applications is in situations where you're mixing solutions in chemistry. We're going to take a look at an example in a minute where you're talking about, just any time you're mixing a couple of liquids and with different amounts of things in them, and to kind of get to a desired result. So, some applications here that we definitely want to take a look at so we know why we're trying to solve these systems. So we'll talk a little bit about how to choose the best method. We've been doing this all along anyway. We'll do a quick review of that. Take a look at some mixture problems, as well as take a look at some other story problems that we've kind of already seen, and just sort of review those as well. Okay, there are the standards we're going to hit. First things first, what method should we use to solve the system? We've been talking a lot about this already. In this system, which is not in your notes, but in this system, we can talk real quick. Which method, graphing, substitution, or elimination, would you want to use to solve this system? Now, graphing has its use and has its time to be used, the graphing method, but by and large, we're not going to really want to use the graphing method very often. Okay? It's not very accurate. If you're fine with that, if you're fine with estimating a solution, then the graphing method is fine too. But plus, it's too difficult to have the right tools all the time to use the graphing method, as far as a well laid out grid and that kind of thing. So not very often we're going to want to use the graphing method. Now, it leaves substitution or elimination. If you look in this equation, we have a y that has a coefficient of 1. In this equation, we have an x that has a coefficient of 1. Either one of those two variables would be easy enough to solve for. Either one of those two would be easy enough to get by itself, to isolate. And that's what we'd have to do to use substitution. So could substitution be a fairly easy method here to use? Yes, it would be. Why are we looking for variables that have a coefficient of 1? Because if we are going to isolate a variable that has a coefficient of 1, then we know we're not going to have to divide by anything later. And if we don't have to divide by anything to get that variable by itself, that means we're not going to create fractions that we're going to have to worry about doing math with, right? So substitution would be fine here if you solve the second equation for x or the first one for y. No fraction fears there. Elimination would be an easy enough method here as well. You could multiply the first equation by -2 to make the y's opposites. Since the x's and the y's are lined up, you could do that fairly easily. Or you can multiply the second equation by -2 to make the x's opposites. Especially, this would be especially easy since the x's and y's again are already lined up. So those are the types of things that you're going to want to look for as far as whether you want to use substitution or elimination. You're going to have a favorite method, and you're going to want to use that method all the time. But there are times where using a different method might make your life a little bit easier. Okay? When are those times? Well, here's some pretty good rules of thumb. Okay? Graphing. Use graphing when you want a visual display of the equation, and sometimes that's helpful, or when you want to estimate a solution. Okay? Again, graphing is not a great method, especially if you want any kind of accuracy to your solution. Substitution. Use substitution when one equation already has a variable solved for. Right? There's no work there. You can just go right into substituting. Or if you have what we call a naked variable. Then you have a variable where the coefficient is 1 and it would be easy enough to solve for it. Okay? Elimination. We're going to use elimination when the coefficients of a variable are already the same or they're opposites, same number, different signs, so we can just add the equations and eliminate. Or we're going to want to use elimination when substitution and graphing just isn't going to be very easy for us to do. Okay? So elimination for me is just sort of the default method. I need a reason not to do elimination, but that's just me. ultimately, any method is fine that you choose. Uh, any method will get you to the same solution. It's just a matter of picking out which one might be easier. Okay, so take a look at these three. These three are in your notes. Take a couple of minutes, jot down which of the three methods you would want to use, and then think about why. Okay, you can stop the video, think about that, write that down, and then I'll talk through these three and which ones you might want to use and why. All right, so the first one here, substitution might be easy enough, okay, to do, because y is already solved for, and you can go straight into substituting, okay, and no fractions that we have to worry about. So maybe the first system, substitution, would be the best method to use. The second one, elimination, would be probably the best method to use, because the x's are already opposites. So if you add the two equations together, they're going to eliminate, and we can go and solve for y and then substitute back in to find x. Okay? This last one, I think, is designed with the idea for us to think about graphing being the best method. Okay? And why? Because we're already in slope-intercept form, and we can graph the lines from slope-intercept form. But we talked about this already. Graphing not giving you the most accurate solution all the time, and not easy to do unless you have a grid and you know, it can make nice, pretty straight lines. Now, we could use the slope. We talked about this before too. When you graph two lines, you don't have to draw super straight lines. You can use the slope to count down or up either line, and hopefully your fingers will get to the same point. But anyway, that's the design here for you to think about using graphing in this third system. I probably still wouldn't, personally. I would use substitution and just go ahead and substitute this 2x minus 1 in for this y, and then clear the fractions and solve. But I think that was the design for that third one. Okay, so just some things to think about. When you have your system set up, take a look and see which one's going to be the easiest method to use to solve. Okay, all right, let's get into our applications here. A couple of these we've already kind of seen some examples of. I'll walk through this first one fairly quickly because this is a lot like the ones that we've seen before. And we want to get to our mixture problems because those can be a little weird. Okay, so number one, a sightseeing boat charges $5 for kids, $8 for adults. On its first trip of the day, it collected $439 for 71 paying passengers. How many kids and how many adults were on the boat? Now, for any story problem, the first thing I try to do is pick out what it is I don't know or what it is I'm trying to find. Right now, we don't know the number of kids or the number of adults that were on the boat. Okay? Now, by and large, the number of kids and the number of adults on the boat are independent of each other. Now, obviously families bring the adults and kids both, and so there is some sort of relationship there, but by and large they're independent of each other, so it doesn't matter how you define these variables. If you let the kids be x, the adults be y, that's fine. Okay? Now, your two equations, where do they come from? Well, there's two situations, one where we count the passengers and one where we figure out where the money is coming from, right? So we're going to count the passengers, and then we're going to turn those passengers, the number of passengers, into the amount of money that was collected. Okay? Well, if we're going to count the passengers and get 71 passengers, that means we counted the kids and we counted the adults and we added those two groups together, right? Since x is the number of kids and y is the number of adults, then our first equation, we can just take the x plus y, and that's going to have to give us 71. That's how many people were on the boat. Okay? Now, I want to turn those counts into dollar values, right? 71 people apparently got us $439. So 71 people is going to turn into $439. Now, how? Well, the number of kids. We collected money based on the number of kids. How much money did we collect from the number of kids? Well, we would take the number of kids that were on the boat and multiply it by 5 because they had to pay $5 to get on the boat. So 5x is where we're going to get the amount of money from the kids. And then for the same reason, we're going to take 8 and multiply it by the number of adults on the boat to find out how much money we collected from the adults. And when I take the money from the kids and add to it the money from the adults, it's going to have to equal the total amount of money, which is $439. Okay? So there's where your two equations would come from and to solve your system. Now, to solve quickly, the x's and y's are lined up. Elimination might be easy enough for you to do. In the first equation, the x and the y are both naked. In other words, they have coefficients of 1, and we're not going to have to divide by anything to isolate one of them. So substitution is going to be fine to use as well. You can use whatever you want. I'm going to use elimination. I like elimination. I'm going to multiply this first equation by -5 so that I can eliminate my x's. Okay? Now, add these two equations. The x's add to 0. 8y and -5y is 3y. And then 439 and -355, when you add those together, you are going to get 84. Okay? Now, 0 plus 3y is just 3y. So I'm just going to divide by the 3. I'm going to ignore the 0 there. And so y ends up being 28. Okay? Which means there were 28 adults on board the boat. How many kids? Well, take your y, substitute it back into either one of your two equations. That one's going to be, the first one's going to be the easiest one to do that for, probably. Subtract 28, and you are going to get 43. Okay? So, in a nice complete sentence, you would write out, there were 43 children and 28 adults on the boat. Okay? Make sure you write out your complete sentence. I'm not going to do that just to save time, but write out your sentence answer. Okay? But there you go. All right. Here's a money problem where we've seen this before. So take a couple of seconds, write out your equations, and then we'll go through quickly solving it, and then we'll get to some mixture problems. Okay, here's how you'd want to set this up, right? We have 30 coins. We don't know the number of dimes. We don't know the number of nickels, so that's what we're going to define our variables as. Because the number of dimes and the number of nickels going into this don't really depend on each other, we can define the variables however we want. We can use x and y. I use d for dimes, n for nickels. It doesn't really matter. Okay? Now, we've got two situations. One, we recount the number of coins. So if I take just the number of physical coins of dimes and the number of physical nickels and added those two numbers together, they're going to have to equal 30 because we know we had 30 coins. So d plus n is equal to 30. Now, I want to convert those counts into dollars, right? 30 coins apparently made us $2.10. So there's the conversion from 30 to 210. All right? Now, how do I take the number of dimes and convert that to dollars? Not cents, but dollars. Well, dimes are $0.10, right? Since they're 10 cents. So I would take the number of dimes and multiply it by 0.10 to find out how many dollars my dimes would give me. Okay? Same thing with the nickels. They're $0.05. So I would take the number of nickels and multiply by 0.05 to find out how many dollars I had. Which is not how we count money. So it's a little weird to think about, but if we're going to write out an equation, this is what we would need to do. Now, I want to show you something here. We've talked about in class that we could always convert the money equation into cents and get rid of these decimals. Okay? That's what I'm going to do here. But I'm going to do it sort of the scenic route so you can actually see what's going on. If I'm going to take these decimals and make them whole numbers, then all three of these decimals I'm going to have to slide to the right 2 spaces. And to do that, we would multiply by 100. Right? Now we're talking a little bit about scientific notation and how to rewrite that. But anyway, if I want to move decimal places to the right, I've got to multiply by either 10 or 100 or 1,000, the number of zeros would equal the number of places I need to move the decimal point. Since I need to move the decimal point 2 places, I'm going to multiply it by 100. When I do that, 100 times 0.1 is going to give me 1. 100 times 0.05 is going to, oh, sorry, not 1. It's going to give me 10. 100 times 0.05 is going to give me 5. And 100 times 2.10 is going to give me 210. So now I'm dealing with whole numbers instead of decimals, and so that might make the math a little bit easier. Okay? Now we got to solve that system. Okay? Now, again, it sets up nicely for substitution as well, and you can do substitution, but I like elimination. So I'm going to multiply the top equation by -5 so that I can eliminate my n's. So 5 times d, or negative 5 times d is negative 5d. We get negative 5n, and we get negative 150. Those add to 0. So I get 5d plus 0 equals 60. Divide by 5, and d is 12. Okay? So that means we had 12 dimes, apparently. How many nickels do we have? We'll take d, substitute it in here for this n. And so we get 12 plus n equals 30. Subtract 12 and 18. So in a complete sentence, we would say that apparently she has 12 dimes, which we could have stopped there. It only asked for how many dimes she had. Okay? So apparently Elvira had 12 dimes. Okay? All right. Kind of the same situation with this t. See if you can't set the equations up with the t. And then we're going to kind of sort of baby step our way into mixture problems. Okay? So stop the video, come up with your equations, and see if you come up with the same thing that I do. Okay, this is what you came up with. A little bit weird in defining your variables, but what we need to know is how many pounds of each kind of tea did he use. So we need the number of pounds of the expensive tea and the number of pounds of the less expensive tea. So the $1.25 tea and the 65-cent tea. Okay? X and Y are going to stand for the number of pounds. All right? So he mixed together a total of 150 pounds. So if I take the amount of number of pounds of the expensive tea plus the number of pounds of the inexpensive tea, that should equal 150. Now, I want to convert the number of pounds into how much money. And apparently 150 pounds of this tea is going to be worth a total of $109.50. So I converted 150 pounds to amount of money cost there. Okay? Now, how do we find out how much the $1.25 tea is worth? Well, if it's $1.25 per pound, then we would take the number of pounds of that tea and multiply it by $1.25. So that's where that came from. And same thing for the 65-cent tea. We take the number of pounds and multiply it by the 65 cents, because it's 65 cents per pound. Okay? So there's your system that you would need to solve. Now again, I've got decimals here, and we have access to calculators, so decimals may not be that scary anymore. But I can clear the decimals, much like I clear fractions, by multiplying by a large enough factor of 10 to move all decimal places over. And I've got to move all of them over 2 spaces, so I multiply through by 100. So again, 125x plus 65y equals 10,950. Okay? And then I'm going to solve these two. Okay? You know what? It sets up fine for substitution, so that's what I'm going to do this time, just to kind of change it up. I'm going to subtract x here to isolate the y. And so I'm going to get y equals 150 minus x. Okay, now I'm going to take this and substitute in for that y. So we get 125x plus 65 times 150 minus x equals 10,950. Now distribute. So we get 125x plus 65 times 150, which gets us 9,750 minus 65x equals 10,950. Combine like terms. Okay, so we're going to get, what, 60x is equal to, I'm going to subtract the 9750 and get 1200. Okay, divide through by 60 and x ends up being 20. So that means we're going to use 20 pounds of the $1.25 tea. How much of the 65-cent tea? Well, we can substitute back in for x here. Subtract 20. Okay, so we're going to use 130 pounds of the other tea. So in a complete sentence, okay, we're going to use 20 pounds of the expensive tea and 130 pounds of the inexpensive tea to create a mixture that is 150 pounds worth $109.50. Okay? All right. So a little bit into the mixture. Now we're getting into a little bit more, right? So Dice Dairy Farms produces low-fat milk containing 1% fat and regular milk containing 3.5% fat. How many gallons of each type should be combined to make 100 gallons of milk that is 2% fat? Okay? So what do we need? We need to know the number of gallons of 1% milk and the number of gallons of 3.5% milk to mix. Okay, and since they don't really depend on each other, again, we can define them however we want. So we'll let x be the 1% and y be the 3.5%. Okay, but x and y are gallons, number of gallons, right? We need 100 gallons. So we're going to take x plus y, which is the number of gallons of each type of milk. We have to add those together to make 100. Now, I want to convert this into the amount of fat. How much fat is in each amount, in each gallon amount, right? Well, if we're going to make 100 gallons of 2% milk, right, then to find out the amount of fat in there, I would take my 100 gallons and multiply it by 0.02, because that's 2%. Okay? Well, the same thing for the x and the y. The x being the 1% milk, x is the number of gallons. To find out how much fat is going to be in that collection of milk, I've got to take the amount of gallons, which is x, and multiply it by its fat percent, which is 0.01. That will tell me how much fat is in that collection of milk. And the same thing with the 3.5%, right? I've got to take the number of gallons in the which is y, and multiply it by its fat percent, which is 0.035. When we take percents and put them into equations, we always make them decimals. Okay? So I'm going to go ahead and multiply out the 100 times the 0.02 because I can. It's just simplifying. Right? And we get 2. Don't really need that guy anymore. Now, I need to start solving my system. But again, I've got decimals in this second equation, and I've got to move this decimal over 2 places, this decimal over 3 places to get rid of the decimals completely. So since I have to move 3 places, I'm going to multiply this equation by 1,000. Okay? Now I'm going to move the decimal places for everything over 3 places. So since this guy's moving 3 places, this becomes 10x. 1,000 times 0.035 is 35y. And 1,000 times 2, of course, is 2,000. Now, I'm going to use these 2 equations. Okay. Again, easy enough to set up either way. I'm going to go ahead and multiply this first equation by negative 10 to use elimination. So we get negative 10x minus 10y is equal to negative 1,000. Then I'm going to add these two equations together. These add to 0. 35 and negative 10 will give you 25y. And 2,000 and negative 1,000 will give you 1,000. We divide both sides by 25, and we would get 40. So we'd have to use 40 gallons of the 3.5% milk. How much of the 1% milk? We'll plug this 40 in here, and you're going to see right away it's going to be 60. Right? Subtract 40 here and 60. And so in a complete sentence, okay, you'd say something like, to make 100 gallons of 2% milk, 2% fat milk, we would have to combine 40 gallons of the 3.5% milk and 60 gallons of the 1% milk. Okay? So that's what we mean by mixture. We had to convert one of the equations into the amount of fat. Okay? Now, at the same time, here's your chemistry example, and when you get to a chemistry class, you may end up using this quite a lot, right? So Mr. Lamb's doing a chemistry experiment that calls for 200 milliliters of a 30% copper sulfate solution. How many milliliters of 60% and 10% solution must he mix to obtain the desired 30% solution? So here's the thing. I mean, you're not going to, if you need copper sulfate solution for whatever reason, right, you're not going to have every concentration known to man sitting on a shelf. It's just not feasible. You'll have a couple of different concentrations, and then you need to figure out how much to mix to get the concentration that you need. Okay? So, how many milliliters is what we're looking for? So we need the number of milliliters of the 60% solution and I need the number of milliliters of the 10% solution. Okay? Now, again, they don't really depend on each other, so you can define them however you want. So let the 60% be x, 10% be y. You can define them the other way if you want. It's fine. But here's our two equations, right? So x is the number of milliliters, and y is so x and y are a number of milliliters, right? How many milliliters? Now we need to make a solution of 200 milliliters. So when I take the amount of each of the individual solutions and add them together, they're going to have to equal 200 milliliters. Okay? Now the second equation needs to be written in terms of how much copper sulfate is going to be in those solutions, right? Since we're trying to make 30% copper sulfate, then to find out how much copper sulfate is actually in the solution, I've got to take the 200 and multiply it by 0.3. And I'm going to do the same thing for the x and the y. Since x is the amount of milliliters of the 60%, I've got to multiply that amount by 0.60. And for the 10%, I've got to multiply the number of milliliters times 0.10. And there are my two equations, a lot like the milk example just a second ago. Okay, I'm going to go ahead and multiply these guys out. Get 60 here. And then again, I'm going to clear these decimals by multiplying by 100. Because I've got to move both of these decimals over two places. And when I do, I get 6x plus 10y has to equal 60 times 100 is 6,000. Okay? And then I got to solve these two equations, these systems. Okay? Again, I'm going to use elimination. Multiply this first equation by negative 6 to eliminate the x's. Add to 0. This is 0 plus 4y. Okay. 6,000 minus 1,200 is 4,800. Okay, now we're going to divide by 4, and y is 1,200. That doesn't make any sense. Aha, because I made a mistake. I can't multiply by -6. I have to multiply by -60. You big goofball. So let's go back and do this again. But it's a good check, right? I realized that this was not going to make any sense. So I had to go back and check my work. Okay? Alright. So let's do this again. So multiply this is -60. Oh, here's the problem. This is going to be 60x here. Now multiply through the top guy by -60. And this is the two equations that you have to solve now. Alright? So now that's going to add to 0. This is going to be -50y. And this is going to be -6,000. Now if I divide by -50, now I have to divide by -50 because it's -50 there, then your y ends up being 120. Now that makes more sense. Okay, so we're going to need, it looks like 120 milliliters of the 10%. How much of the 60%? Well, you could plug this back in, or you can do the math pretty quickly in your head probably. But if we have to have a total of 200, and we're going to have 120 of one solution, that means we're going to have 80 of the other. And so in a complete sentence, well, first of all, we're going to check our work and make sure that's right. Okay? But in a complete sentence, we're going to say we're going to need 80 milliliters of the 10% solution and 120 milliliters of the 60% solution. Okay? All right. Take a crack at setting up the equations for number 6. I'm not going to solve this out all the way. Hopefully solving the system is going to be all right. I'm going to set these up, do my moving of decimals around if I need to, and then I'll give you the solutions and I'll let you try to solve them. All right? So try it out, stop the video, and see if you're right. Okay, so that's what you should have come up with. If X is going to be the quarts of pure orange juice, Y is the quarts of the drink, right? If we add those two amounts together, they have to equal 5 quarts, so that's the first equation. And then to come up with the second equation here, we have to convert that to the amount of orange juice in the drink, right? So we want 40% in the 5 quarts, so we had to multiply the 5 times 0.4 here. Now, if X is pure orange juice, then it's going to be 100% orange juice. So we take the quarts times 100%, or 1, if you convert that to a decimal. And then Y is the quarts of the drink, so to find out how much orange juice is actually there, we take the quarts times the 10%, because it's a 10% drink, so 0.10. And then we had to multiply through by 100 to clear all of the decimals by the time we were done simplifying. And there's, I did elimination again, and I got 3.3 and 1.7, which means that in a complete sentence, again, you are going to say, all right, we need 1.7 quarts of pure orange juice and 3.3 quarts of the orange drink. Okay? All right. So hopefully that helps. Homework's out in Canvas. Make sure you get that turned in.